So today we're going to use the finite difference method and do an introduction into it, and we're going to use it to figure out how do we figure out what are these partial differential equations and how do we estimate derivatives using this specific method. So it's used to solve partial differential equations. These can be things like the heat equation, it can be fluid dynamics equations, it can be elasticity, anything that has this type of a partial derivative. It can be used to solve it. It's just one of the many computational methods that's used and is one of the more simple ones to implement. And so what we're going to look at is we have this general curve f of x. And so we're going to look at how this is f of x. We know it at three specific points. We know its value at x1. We know its value at xi minus 1. We know its value at xi. And we know its value at xi plus 1. And so what we are going to be solving today is we want to know what is this derivative, so df dx, at this specific point. So the way we can write it down is we're first going to write it down. So this is going to be, so it's going to be df dx at xi. And so what this is saying, it's saying how does our function f change as we change our variable x. So you can see here in our curve, so how does this change? This is just going to be our slope. It's going to be the slope of the line, but then we're going to want it at this specific point. So at this specific point, what is its slope? And so there's, if we know the equation of f, we can always use calculus to take the derivative. The total derivative, and then plug our numbers in. But here, what we're going to use is we're only going to use these points that were known to come up with an estimate. And so the way we can do this estimate is, so remember slope, it's just rise over run. So it's how much does the height change with the distance. And so we can just estimate this. This is going to be, we're going to look at this point minus this point. So it's going to be, we'll write this as f of xi plus 1 minus f of xi. So that's the change in the height from this point to that point. And then the bottom, the denominator, that's just the change in the distance. So that's the value of x at I plus 1 minus the value of x at I. And so if you remember from our last video, what we had seen is we saw that, okay, if we take these equations, a function, we can discretize it and find it at specific points. And so these aren't just variables, but we can always plug in what is the value of x here. What is the value of x at I? What is the value of x at I plus 1? And so on. We can figure out what is the value of this function. So this point here is just the same one over here. And if you remember, we also said that, okay, we're going to use a uniform spacing between our points. And so in this case, our uniform spacing, this here, is just delta x. There's delta x from this point to this point. There's some other delta x from this point to this point. So this could, if this point was 1, this could be 1.5, 2, 2.5, and so on. And so we can then rewrite this to give us our equation, which is then going to be df dx at xi. That's just equal, so the numerator is going to stay the same. And then we're just going to replace this denominator with, rather than having to keep track of the x values, we can just divide by delta x. And so if we know these points, we can use them to estimate our slope at that point and give us the value of this function that we were looking for. This specific method that I just showed here, this is what's known as right differences. Right differences because we've taken the value of our point and we've looked at what's the value to the right of it. So this is right differences. We can also then, but you see we could estimate our slope in different ways. We could use it here and use the point to the right. We could have also done it and used the point to the left. And so rather than being I plus 1, this would be just I and I minus 1. That's what's known as left differences. But then there's also a third method that we can use, which is rather than just using one of those points, why don't we use both of them? You know, we're going to be able to get a more accurate estimate if I don't just know where it's going, but where was it before. So if we can use both of those points, we can use those to figure out to give us a different estimate value. And so for that, what it is, so in this case, then we'll get df dx. So it's still going to be at the same point, and then rather than using xi, we'll use xi minus 1. So we'll rewrite this equation. So this is f at xi plus 1 minus the value of the function at I minus 1. And then we just replace our x values. And so you can see that this numerator is just slightly different than the one above. But the denominator, since we're no longer going from one point to the point next to it, but we're going from one point to the second point over, then you see that we have one delta x here, and then another delta x here. So this subtraction just becomes 2 delta x. So there's 2 delta x to go from this point to that point. So we'll just rewrite that. And so whereas the value of the estimate that we used before, whereas this was the right differences, this equation that we've just derived here, that's what's known as centered differences. Centered, obviously, because we want to know the value of our point, and so we're looking, it's even on both sides. It is sort of an interesting equation in that you can see that we don't actually, to calculate the derivative here, we don't end up using the value of this point. We use this one, so we use xi plus 1. We use our other value, which is at I minus 1, but we never actually use xi to calculate the value of its derivative. But this actually ends up, we'll do the Taylor expansions. We can use Taylor expansions to figure out how accurate are these estimates of our derivatives. How accurate, do they then scale as, if delta x increases, is it better or worse? And so what we see is that this actually is a much better estimate than this other one. This ends up being second order accurate. Yeah, whereas this is only first order accurate, so it's much less accurate. And so this is why this is commonly used. And this is what we'll be using in our project in class. So this is the right differences, the centered differences. Finally, the last thing we can do is we can also do, so these are the first derivatives. We can also do the same thing for our second derivatives. So we can just come up with an equation using these points to figure out, doing the same method, what is an estimate of the curvature, the second derivative. And so we'll just write that one down for completion. And so the second derivative, that is going to be so remember, this is how we write our second derivatives. So it's the partial derivative of x squared over df squared. And then what this ends up being, and then this is remember this is at a specific point, so this is going to be at x sub I. And so then what we end up seeing is that this is just equal to, so it's the value of our function at xi plus 1 minus 2 times the value of our function at xi plus the value of our function at xi minus 1 all over delta x squared. And so this is what, just like what we did before for our first derivatives, this is what we can use to estimate our second derivative. And so what we'll be doing in class or in homework in our assignments is we'll look at some different functions and know, okay, if we know these values of our points, or if we are given some initial positions, then we are going to use these types of equations to come up with estimates of our derivatives. We'll also look at, okay, if we use something, a known function, like a sine function, then we should be able to compare our estimated derivatives with the calculus derivative, and we'll make sure that those are the same. Computationally, that's always a good plan, just to make sure our equations are right, our code is right. But this is sort of the basics to how to do the finite difference method. And so then what we'll be looking at later is sort of then some more specific applications and how to go further with this and go into multiple dimensions.